So welcome to the second installation of the Summer 2016 Student Exit Presentations. Today we'll be hearing from Gale Curry, a graduate student at Northwestern University who has been working with the Autonomy Incubator on some flocking and swarming techniques. Gale Curry.
Thank you. Okay, so like Danette said, my name's Gale, and I have been working on some swarming algorithms this summer, and I've been implementing them on nano quad rotors. So this is just a quad chart. This is how we keep track of our progress that we've made this summer. Basically not super important right now, but I'm going to move on to explain basically what I've been doing this whole summer and what's summarized here. So I'm going to give you a little background on swarming, and the main swarming algorithm was thought up by Craig Reynolds in 1987. His paper was called Flocks, Herds, and Schools, a Distributed Behavioral Model. It basically just lays out super simple rules that these boids, bird androids, I'm going to refer to them as boids the rest of this, they sound weird, but it just means bird android, how they can follow simple rules to create formations and swarms. So basically the rules that they have is that each boid can have a 2D or 3D position. In my implementation I've only done 2D, but you can have 3D as well, and also a velocity. And these boids, they can see all of the other boids around them within a certain area, or they can see all the boids in the entire swarm. So since my swarms were pretty small, I decided to let them see pretty much everyone else around them. And so that's kind of interesting because it shows how you can create really interesting swarm behaviors, even with limited sensing. So if your robots don't know the exact location and whereabouts and speeds of everything else around it because sensing is limited, then it can still create these really cool swarms. So the way they decide where to move around is based on these weighted velocity vectors, which the first one is cohesion. So basically, like in a regular swarm of birds, they will look around, figure out which other birds I can see, where are they, where do I need to move to get towards this center of mass. So that's what you see up there. COM is center of mass. They just figure out where that is, and this velocity vector just tells you how to get to that point. The next thing they do is aversion, which makes sure that each of the boids don't run into each other. So they check each boid around it and say, where are you? How far away am I? If I am within this area, which I call nearby, is just a radius of a circle where it does not want these other boids to be in. It says, get away from me, so I'm going to move out of your way. And they'll add those up for each boid that it can see. So as you can see down there, that's what that one is doing. And the final main velocity vector is alignment. So where are my friends going? I want to start going that way too. If maybe just one boid in the flock knows where the target is, then the other ones can just be like, okay, sure, I'll follow you guys. We'll all want to go in the same direction. So heading is super important, and it makes it so only, say, just this leader guy knows and can see, is within sight of its goal, and the guys farther back in the flock can still figure out where to go. So what you do in the end is you add them all together with various weights of your choosing. And what's really cool about this is that you can tune this to many different kinds of situations. So if in your situation you really want these guys to not hit each other, which is pretty important when we're working with robots and drones here. So you can up the weight of the aversion vector, for example, and that will make it so that it prefers aversion over pretty much everything else. Maybe you don't care that they stay in so much of a group as long as they don't hit each other and maybe they don't hit other things. So here, I think I probably just put them kind of equally, and this is them starting at initialized random positions. They can see everyone in the room, so they all kind of go to the center of mass place and just hover around each other. So what else is cool is that this can be extended super easily. So you have those three main velocity vectors, but you can add a ton more. So what I was working on was a couple different things we could do. So first I added a goal. That star over there is the goal where these boids want to go. You can see they're trying to make it through these walls, and they don't quite make it because I hadn't implemented obstacle avoidance yet. So they run into these walls and they disappear. That's because they are crashing and they are gone. So this is pretty cool. And you can also see here I added the what I call the sphere of influence. It's just the circle around each Boyd where it can see all of its friends. So farther out, as long as they can at least see one other Boyd within its sphere, it can usually find its way to the swarm. But sometimes if you make that sphere too small, they form multiple mini swarms, which depending on what you want to do with them could be good or could be bad. You might not care, and it might be interesting to you to have multiple swarms just form out of just naturally. So the next thing I added was obstacle avoidance. Now you can see they are seeing those little brick walls and they are avoiding them to get to the goal. So this time nobody crashes and they all make it to where they're trying to go. And in all these cases, there's no leader yet. So the next thing I added was leader following. These guys are following the little dot, which I control on my computer, which is the arrow keys. The leader following is super interesting to me because not only can it be led by just me on my computer, but it can be led by drones, people, lots of cool things which I'll talk about in a little bit. They can also create formations. I set it up so I can have an X formation, a V formation, and a straight line formation, which is pretty fun to see. I will hopefully in the near future get them flying in this formation. Just visually will look really cool. But then that's really, formations are really nice if you want to take sensor data of a large area, so these guys can be evenly spaced and get really nice sensor data. And another thing I started working on, which didn't really quite finish, I'm working on dynamic formations, and these kind of formations are better than the static ones for if you're trying to get into smaller areas. So if I had a formation that I wanted to kind of follow me, and like if I wanted to go away formation like that, they can get into smaller areas. So like I said before, this program is leader agnostic, so it can follow anything that has Vicon markers on it. So later on, you'll see a video of me wearing the helmet with the Vicon markers and having having one of the guys follow me around. So what's really cool is that we can put these Vicon markers on one of our bigger drones and have it fly around, and then the small, tiny quadrotors, the crazy flies, can follow it. So it's also follower agnostic. This can be hooked up to the AR drones also, and in addition to the crazy flies, which I have been working with. The whole project kind of had a lot of pieces that I wanted to fit together. So this is just kind of an overview of how those pieces came together. We have a Vicon system in the AI, and the Vicon system is able to see the positions of anything that has Vicon markers in it. So the Vicon publisher will publish the XYZ position of any of my leaders. So it will tell the flocking algorithm where this leader is. So I can hook it up so that my algorithm reads in the leader's over here, your little flock is going to follow you. It can also directly publish the XYZ positions of each of the followers. In this case is the crazy fly, and that is what is used by the controllers to figure out to hold position constant. So then my flocking algorithm tells the controllers where the desired position is, and then all the followers will stay in that position based on this controller. For the crazy fly specifically, after it goes in the controller section, the crazy fly interface, which was built by another intern last year, talks to the crazy flies, which talks to a crazy radio, which then talks to the actual crazy flies. So it's kind of a complicated process, and each part needs to be working perfectly together, which kind of makes it a little finicky, but we got it to work well in the end. So we have two controllers here, you probably noticed. There was already an existing Simulant controller last year, which I used a little bit, and then we also tried to create a new C++ controller because it's more portable, and that's what I was working on, which is not quite finished, which is why it is in yellow. But either way, we can pop it into the Simulant controller and test this out. So a little more about the crazy flies. A lot of you guys have heard of them. They are crashing around a lot. But one of the things that makes them so interesting for research is the fact that they're completely open source. So that's why they're frequently used by universities. Most other quadrotors of this size, they don't have such an online community. You can go on the BitCraze GitHub and find all of these libraries that people have made. The Crazyfly interface that was made last summer was based on a Crazyfly C++ library. They have Python libraries, they have all these different things that all these researchers have made already that you can use open source, which is really cool. So basically the only thing that we had to do to these was add those 3D printed bumpers around to hold these Vicon markers. Since these guys are really small and can't hold much weight, we tried to keep the weight down. So we put a minimum of 3 or 4 of these Vicon markers, which we also had to 3D print and put the Vicon tape on separately, which was an interesting job, but it worked out in the end. And hopefully we're thinking of doing some more designs of different bumpers to see how much of the space we can utilize and how many different markers we can place in different areas, because the Vicon system needs them to be asymmetrical. So the more surface area we have on these bumpers, the more different combinations of Vicon markers that we can put, and therefore the larger swarm we can make. So a little more about the Crazyfly controller that I worked on for a good portion of the summer. So the Crazyflies already have onboard attitude control. So all we have left to do is give it position control and send it angle commands, which is pretty nice that they at least have that part done for us. How we did this position control was we made a simple PID controller, PID proportional integral derivative, and just basically implemented that first in Simulink, and then I tried rewriting that into C++, which takes a long time if you know about controls. Tuning takes a super long time. Simulink was already pre-tuned, and that's why that worked quite well, really fast. When I tried to do it, the games didn't translate from Simulink World to C++ World quite so nicely. So that's why you can see I had lots of crashing and lots of crazy flights that were flying just everywhere. Not really position control, but it got a lot better near the end of the time that I was here. And hopefully when I have more time later, I'll be able to perfect this and we can use a C++ controller, which would be great because then it'd be a lot more portable than Simulink, which you can only run on a MATLAB computer. So here's a little video of the day I finally got it to fly. This was right before the flood, so the only videos I have here are from Snapchat. I'm sorry. Not quite as professional, but I'm wearing the helmet, so the Vicon system sees where I am, and in my program, that little pink dot will be represented by my position in the Vicon area. And if you can see the little guy flying right next to me, he is held at a constant height of 1 meter, but his X and Y position is, I think he was somewhere in an X formation. He was making a formation just by himself because I was trying with just one crazy fly. But by the end of the summer, before the flood, we got it flying, we got his position to be controlled, which was really great. So it should be simple to just add the rest of the crazy flies on. Okay, so in general, what's so great about swarms and flocking? Why even go through all of this? One of the really great things about swarms is that they can be led by intelligent leaders and really simple followers. So those crazy flies don't have much computing power on board. They can't do a ton, but they can accomplish really complicated tasks if they just have one intelligent leader. So for example, it's kind of hard to see, but here in this video, the pink dot is actually being controlled by one of our larger drones called Notorious, which is not this one, but it's about the size of this drone, which is pretty large. And these crazy flies weren't flying out there, but virtually they were following him in a V formation. So we could have one of these larger drones out there doing tons of computing power, doing all this stuff, avoiding obstacles, dropping off things, and then these really simple crazy flies who don't know much could just be following it around, which is really nice. And these formations also, I'm hoping they'd be good at flying through tight spaces. So making through small apertures, making it through windows, stuff like that, that'd be difficult for larger guys to go through. So I'm hoping that swarming behavior could be used in like search and rescue purposes, getting through small windows, getting into houses, stuff like that. More integration possibilities that I'm hoping to work on later is integrating it with the Holy Grail with a lot of the other interns, what they've been doing this summer. So the end goal, the end result of the Holy Grail was that the user was able to plan this path and they were able to fly it. So this was the leader drone. I could extremely easily tack on my algorithm to their work by having all of their work tell this leader drone where it wants to go, all this specific user-generated data, and then my guys, all they have to do is just follow it. Super easy, super great. And then it could also really easily be included in obstacle detection and avoidance algorithms that a lot of the other PIs have been working on here. Because once they know where an object is, they can also avoid it. So if they have a leader who can detect an object, as long as these guys can be sent back, and they will also avoid that object when they're following a leader in a swarm or a formation. So lessons learned. I had a lot of more programming experience than I expected. I learned about DDS, which I had never worked with before. I was able to bridge Python and C++, which was kind of cool because those are my two favorite languages. I worked with Simulink a lot, and I learned that controllers are really hard, that crazy flies are really difficult, and that arranging Vicon markers is an art. I just want to thank everyone here, Danette, my mentor, Benlock and Kyle for all your programming help, Kevin and Jacob for all your DDS help, Javier for his crazy fly wisdom, because he is the crazy fly master, and all the AI team for their support.
Any questions for Gale?
A couple. The Reynolds algorithm.
Mm-hmm.
Did you find much difficulty in implementing?
Implementing it?
Yeah.
No.
Okay. So
because it was pretty simple.
Right.
So and my that was just my interpretation of his algorithm.
Okay.
That was not a word for word.
Did you see any I don't know, issues with that algorithm? Anything that could be improved or anything that gave you a lot of trouble?
I'd say his algorithm is good for quad rotors specifically because they can move. I talked to Kevin about this and I told him, oh, you're working on swarming as well. Why don't you take a look at Reynolds' algorithm here? And the one thing that his algorithm uses is that it assumes that each void can move pretty much anywhere with no restraints at all. And the real world isn't quite like that. There's no, maybe it's harder to go this way or harder to go that way. And it doesn't really incorporate many real physics of the voids of these quad rotors. It doesn't take any of that into account. So it's basically just a pretty rudimentary, where do I want you to go kind of situation.
Okay. Did you look at any other algorithms like Hepner's or Bayes, anything like that?
So I have a question. Yeah. So you, at the beginning of your presentation, you talked about how you made the decision for one-to-one connectivity between all the voids in the system, right? Because there were so few of them.
Yeah.
So, but you also acknowledged that as that number increased,
Mm-hmm.
this is probably a solution that doesn't scale.
Yeah.
Right? Where do you think, given the application that you've chosen, right? So given
Mm-hmm.
this instantiation, where do you think that knee in the curve is? Where do you need to start thinking about other
Like this is too many.
other networking infrastructure approaches? Yeah.
I'd say once you get out of the place where it also depends on the size of these voids. So if you have a flock of really large ones, you can get away with a lot less. So if you're thinking really small, like hundreds of these guys, the swarming will start forming kind of behaviors that you can't control and that you don't want. So I'd say once you get up into the hundreds, you would want to be thinking about other ways, adding more control to these. Because the way I have it set up now is not letting them basically do what they want, not tons of oversight. Once you get up, even into the 50s, you would need to add more safety and more control.
Why? Why do you think that is?
Because once they can't see, if you're taking into account that they can't see everyone, if it knew at all times where every other single one in your swarm was, then you wouldn't need that control. But once you get to the point where you don't know everything about every single one in your swarm, and you have a swarm of 50, and you start breaking off, If,
So is that what you were pointing at when you were talking about sort of, I don't remember the term you used, but kind of subflocks?
yeah.
Is that the behavior you're talking about?
Yeah, so that could be what happens. So maybe it breaks up into subflocks. One flock can see the goal and starts going there, and one flock is kind of far away, breaks off, does its own thing, does not know where the goal is, does not know where it's going, and just kind of wanders away. If you're fine, if these are quads that you don't care about, which is not usually ever the thing, if you think of these more disposably, like actual birds are, birds kind of don't care as much about the single life of every single bird. That's the way of life. So if you want to keep every single one of your quads safe and you're scaling up to huge, huge numbers and they can't detect where every single one of them is, then yeah, you're going to start needing extra control in there to tell them you're not within range of your friends, you need to go back. And as long as they stay in one flock, things are going to be fine, but once they start breaking up is where you'll get lots of issues.
So Reynolds doesn't take it into consideration at all? So you can easily break Reynolds' algorithm? So you're saying that you can easily break Reynolds' algorithm?
Break it? Well, if his goal is to just have his flock not run into things and make it to the goal, then maybe it might not always make it to the goal. If his algorithm is just to say, I have this interesting behavior of these birds and I can get them to move interestingly, then it doesn't break his algorithm. Because it's interesting to have all the subflocks and see which ones form just naturally. That's interesting. But his algorithm doesn't quite state what the end goal of it is. It's just this is interesting to see these birds move in this way with such simple rules and they do something interesting.
Yeah, that's because the only one, so when he started this, the only people that care about this, and primarily it's still the same way, are etymologists in simulation.
Yeah.
So they were doing this all for natural flocking
Yeah.
studies, and
Yeah.
not necessarily implementations of quads. The fact that it's good that you're implementing on the quads is, a lot of people don't do it, so it's very novel still. And there's other methods like fuzzy methods, fuzzy controllers that actually take all that into consideration. But yeah, that's very interesting. That's good work.
Anything else for Gale? Great, thank you, Gale.